Hey everybody, welcome to the video on proving a few more examples. In front of you, I have some examples that you can try to prove. I will also do the domains for these as I do the proofs. So if you want to take a moment and try them yourself first, I suggest hitting pause. Otherwise, I'm going to jump right into starting them. All right, let's go. So on that first guy, I'll first start with the domain. So there are no functions that show up like tan, cotan, sec, or cosec. So there's no issues just by a function showing up. Now I do have two denominators. So one denominator is cos x plus 1. So that's not going to be able to be 0. And one denominator is sine x. So that can't be 0. Sine is 0 at 0 and pi. This would be cos x can't be -1, which is also at pi. So I only have to get rid of those two. And they are evenly spaced. So my domain restrictions would be all real numbers except x cannot be 0 plus n pi. So I'm just going to say n pi since it started at 0. Okay, so there's my domain. Let's go over here to the proof. So obviously, I think you guys can tell that the left-hand side is busier. The right-hand side is just 0. And typically, I'm going to want to put my two terms together to form one value. And that usually requires me to do common denominators. But here, making the common denominator of, say, cos x plus 1 times sine x seems kind of silly because that's not really going to help me get anywhere that's efficient. So that's not going to be my plan. What I do notice is that cos x plus 1, or rather, I'm going to be thinking of that as 1 plus cos x, that conjugate would be nice because I can't use the Pythagorean with it because it's not squared. So I'm going to multiply the top and bottom by the conjugate, and I'm going to go ahead and switch the order on the bottom to 1 plus cos, because again, it's addition, so it doesn't matter. And the reason that I'm doing that, I'm going to kind of just work with this fraction for a second, and I'll add this one in a minute. The reason I'm planning that is because the bottom here will become 1 minus cos squared. And then, as you know, the bottom can then be replaced with sine squared. So that's where I'm headed because I'm like, ooh, that's a good idea. Also, remember, you're not multiplying out the part that's non-conjugates in the hopes that you can simplify something later, which I can. Here I have a sine over a sine squared. So I'm going to be able to simplify that top to 1 minus cos over just a sine. And why is that so great? Well, this term was just over sine. So basically, I've created a situation with common denominators without actually having to work with both of them or manipulate both of them. So this is all about planning and forethought. So sometimes you go to do it and it worked, and sometimes you go to do it and it doesn't work. Okay, so then these are both over sine x. Let's add them up. I get 1 minus 1, so the 1's cancel. Negative cos plus cos, I get 0, which is why your whole proof comes out to 0. Okay, next guy. All right, let's start with the domain. First of all, tangent shows up, and because tangent merely is present in the problem, that means, because tangent shows up, tangent, remember, really has a denominator of cosine, so if tangent shows up, cos can't be 0. But then the problem also has a denominator as well that I have to set equal to 0 and see if there are any places. And this would end up giving me tan squared can't be 1, which I can solve, which means tan can't be plus or minus 1. Make sure you get the plus or minus. So when is cosine 0? Cosine is 0 at pi over 2, 3 pi over 2. And tan is 1 and negative 1 at both pi over 4, or at all the pi over 4s. Because they're not all evenly spread out, because I didn't use the x-axis part, I'm going to have to write them in two separate pieces. So x can be anything real, except I'm going to start with the pi over 4s. Pi over 4 plus, and then it's every 90 degrees or every pi over 2. And then it also can't be this guy, which is pi over 2, and then that repeats every pi. So plus n pi. All right, so there's our domain. Now let's get to the goods. So over here in the problem, a couple of things that jump out at me at first is that I have a fraction and I have not a fraction. I have a lot of squared variables, which makes me think about Pythagorean identities, but the top is not one, cos squared plus sine squared is, and the bottom is not one. Dang. 1 minus tan squared is not. 1 plus tan squared would be. So if no Pythagorean theorems work out and there's no way to really, like there's nothing that I can do to the denominator to really make it too much nicer, I have a couple of options here. I do notice that my denominator, if I were to change it into terms of sine and cos, is really this. And the reason I point that out is because if I did try to put these two together to kind of see what I'm dealing with, I end up with this guy would have to get multiplied by a cos squared over cos squared. So in the denominator, I would have cos squared minus sine squared over the common denominator of cos, which looks kind of promising because, right, because the top has that same thing. So then I can multiply by the conjugate. Now be careful. The conjugate is of the entire denominator. So there's your major fraction bar. So I'm going to multiply by cosine squared over cos squared minus sine squared. And now I think you can see that both of these are going to cancel, and I'm just left with cos squared. Cool. Another way that you could have done that, maybe seen that, is you could have said to yourself, okay, I want to kind of manipulate this denominator. And so like I know tan squared has a cos squared in it. So another way you could think of attacking this is by multiplying the top and bottom of the fraction by cos. And again, the reason I'm going to do that is because then it will get rid of the cos in that one. So I'll just show you this real quick. You don't have to do it this way. Make sure you're using those equals signs. So then that would give me, now I would leave it factored out of the top because I don't know where that's going to go. And it gives me a cos, which is something I want on the top anyway. So then let's see what I get down here. I get cos squared times 1. And then cos squared times tan squared, because of the fact that tan is really over cos squared, becomes sine squared. And then I think you guys can see how that also would cancel. This whole thing would cancel with the bottom. So a couple different ways you could do it. Oops, I skipped one. There we go. Okay, so let's do the domain for this guy. There are no denominators, but tangent shows up. So remember, if tangent shows up, then its denominator cos can't be 0. So we're talking pi over 2 and 3 pi over 2. So x cannot be pi over 2 plus n pi. That's how far they are apart. Okay, let's do some stuff. Okay, so when I look at this question, I see no fractions, right? But I do see 2 terms and 1. It's much easier usually to go from 2 terms to 1. So I'm going to work from the left. And there's no trig, I mean, there are some trig identities I could use, but it's not necessarily going to help me get where I want. Like I could replace this with sec squared minus 1, but like introducing sec squared isn't going to be helpful. I could replace sine squared with 1 minus cos squared, but again, that's not going to help me get where I want. So I could try looking at it in terms of sine and cos. So that's my plan. Again, many ways to do this question. So this is where I'm going to head. Okay, if I want to take 2 terms and put it into 1, I need common denominators, which means this would need to be multiplied by a cos squared on top and bottom. Right, now I have common denominators. Okay, so then I have sine squared x minus sine squared x cos squared x on top over cos squared. Okay. Now, looking at where I can go with this, I have a couple of options. This is where I'm trying to go, right? This can help me tremendously. This means that I need a sine squared and I need a tan squared. If you look at the top of this, do you guys notice how there's a sine squared in both? If you know you need a sine squared in your final answer, factor it out, because then at least you'll have the sine squared out there ready to go and you can see what gets left over. You see what I mean? So now I have this sine squared, which is ready to go here, which means all this other stuff must somehow become a tan squared. So let's see. Well, 1 minus cos squared, as you guys now know, is sine squared. And then you can group together this sine squared and that cos squared to become a tan squared. And there you go. So it does help to see where you're headed, right? Again, remember, after I do them, you try them again on your own. Like I would go back to the very beginning slide after I'm done with this and do them all again without help, without looking at your notes and see how you do. Okay, 17. Whoo, this is a doozy. So, first of all, domain. Nobody shows up that's a problem. Tan, cotan, sec, cosec. But I do have some denominators. I have 2 plus cos x equals 0, which means cos can't be negative. Oops, can't be 0, so it can't be negative 2. Good news, cosine only fluctuates between 1 and negative 1. So there's never an angle that should give you negative 2, so there's no restrictions for that part. Now this one, technically, I need to be able to see if that's 0. So I think most of you can see where we're going to go with this. I would have to factor this denominator to see if there is any time that it's 0. Okay, so let's see. I would have cos x. Remember, you can factor this just like normal. It's like having x squared plus 3x plus 2. So I'd have 2 and 1, and they'd both be positive. Okay. So we already know, this one is cos x plus 2, which is cos x equals negative 2, which again, their cosine can't be outside of negative 1 to 1. This one is cos x plus 1 equals 0, or can't be 0. So this is cos x can't be negative 1. Now, careful. Cos is only negative 1 here. This is positive 1, so I only need to leave out pi. So when I do my domain, all reals except pi, and then I'm going to have to go all the way around back to it, which would be adding 2 pi. So that would be plus 2 pi n. Okay, but that's it. Then I've taken care of both denominators. I'm good to go. Now I can solve the problem. Okay. So this part of doing the domain kind of helped me get an idea for maybe where I would head, because I could tell that this denominator was going to factor. So that's the first thing that I did. I actually started on the left. I thought that the left was more complicated because of the factoring. So then that meant this factored into cos x plus 1 and cos x plus 2, which we saw from over here. Okay, well, the good news is I have the 2 plus cos x. That was one of the things I wanted. So that was also kind of helpful in the factoring. So that guy I'm going to keep where it is, which means I need to get the rest of this to change. Well, if I need to cancel out a cos x plus 1, then maybe there's a way to get the top to look like some version of cos. And there is. That's an identity, right? 1 minus cos squared. And you can either leave this the way it is, or you could reorder this if you want. It doesn't matter. I'm going to match it to the other side, so I'll go ahead and reorder them. When it's addition, it doesn't matter. What does the top factor into? Yep, 1 plus cos, 1 minus cos. And then I think a lot of you probably already saw where this was headed, but then those two cancel just as you had hoped, and we get our value. Okay. Okay, let's take a look at 6. So 6 has got a lot going on. 6 has, let's do domain first. Cosecant shows up, which means sine can't be 0. Tangent shows up, which means cos can't be 0. And cotangent shows up, which means sine can't be 0, but we already took care of that. Then we have a denominator, tan x plus cotan x can't be 0. You can solve this pretty easily by just multiplying everybody by a tan. That would give me tan squared plus 1 can't be 0. When I try to solve this, I get tan squared is equal to negative 1, which I can't take the square root. So basically what I'm saying is that this part right here, there's never a time it's going to come out to 0. So this doesn't add any issues. I still have these guys. Cos being 0 is here. Sine being 0 is here. So these are all the pi over 2's. So x is anything real. Make sure you start with that. But then x can't be 0 is my first one. So again, you don't need to write the 0. I'll show you it. And then it's every pi over 2. So, pi over 2n or n pi over 2. Again, I don't really need the 0. So I would just probably say pi over 2n. And then n is an integer. Okay. So let's head over to the problem. So in this problem, we have a fraction on the right and cos squared on the left. Obviously, the right is busier here, so I'm going to start there. Now, one of the things that I notice about this denominator straight away, nobody's squared, but these two have a relationship, right? They're conjugates, which means if I were to multiply by either tan or cotan, one of these would become a 1. So that's my plan. These are the kind of things you're going to start thinking about, folks. And the reason I'm going to do that, and I always kind of try it in my head and see if it's going to be nice first. So like in my head, I would have thought, if I multiply by a tan, what do I get? Well, I get tan squared, and then tan times cotan is 1. And that is replaceable with somebody, right? Sec squared. And guess what? A sec squared in the denominator is who in the numerator? Cos squared, which is what I want. So I'm hopeful that this is a good idea. So now I just got to see what happens with the top. Okay, so on the top I have tan x times cosec x times cos. So let's reduce this. And it might be helpful for you, if you're still getting used to these, to rewrite these in terms of sine and cos, right? Okay, so I'm here. So look, the sines drop, the coses drop, you get 1. Now it makes sense because the top is 1, so when I bring it up and get cos squared x, that is in fact what I wanted. You gotta look for those things, those conjugates, not conjugates, excuse me, reciprocal functions, those reciprocals of each other make a difference. I might have been saying conjugates now that I think about it, but I mean reciprocal functions. Sorry guys, reciprocals. When you see reciprocal functions like this, you should be thinking, okay, like, is there a way to me to maybe get something that's Pythagorean that I can work with? I'm pretty sure I was saying conjugate, so I'm sorry. I mean reciprocal functions. Okay, last two. And this guy, let's talk about domain restrictions. Tangent shows up, so cos is out, being 0. Cotangent shows up, which is a sine in the denominator, so that's out. And then I have some denominators. So I need to set cotangent plus 1 equal to 0. I need to set tangent plus 1 equal to 0, or solve for when it isn't. So this would mean I can't have, this would mean I can't have cotangent any place, any angle where cotangent's angle would be -1, and I can't have any place where tangent's angle would be -1. Okay, so let's think about where that is. Cos being 0, here and here. Sine being 0, here and here. Cotangent being -1 is actually the same place that tangent's -1, and they're -1 here and here, those two pi/4s. Okay, so I'm going to have to write these separately. So I can be anything real. I'll start with these 4. These 4 are evenly spaced, so I'm going to do them together. So x can't be, this would be 0 plus pi n, or pi over 2n. So I'm going to do n pi over 2. So that would get all 4 of those. But then I also can't be this one. This one is 3 pi over 4. And then it is evenly spaced with this one. And those are how far apart? Pi. So n pi. Okay, so there's your domain. So let's go back over to the problem. First things first, I've got a couple of fractions that I'm adding together, and I get 1, which is a pretty easy one. So I'm probably going to make common denominators. But instead of jumping into immediately using the 2 denominators I have, I'm going to look at them and just see, is there anything that I could maybe do to make this easier before I start doing common denominators? Well, yeah, once again, these are conjugates. So I can make this question look a lot simpler. Again, I'm thinking like just what would happen if I would multiply, say, this guy by its conjugate, right? Is that helpful? Maybe the answer is no. Well, tan times cotan will be a 1, and tan times 1 will be tan. Look at that. You have now you already have the exact same matching denominator, and you didn't even have to do any crazy algebra. Look for that stuff. Oops, I forgot. Sorry, the top needs to be tan. There we go. Right, because we multiplied by tan. So then, okay, so then I put everybody together. On top, I have tan x plus 1. On the bottom, the common denominator is 1 plus tan x. What? They're the same. We did it. If you immediately started changing things into sine and cos, you're making it harder than it has to be. Doesn't mean you can't do it. I'm just showing you a very efficient way of doing it. All right, last one is a doozy. Let's see what we've got. Cosecant is in the problem, which means sine of a can't be 0. Cotangent is in the problem, which also means sine of a can't be 0. And then this denominator is 1 plus cos a, so that can't be 0, which means cos can't be -1. So let's think about where this is. Sine is 0 here and here, and cos is -1 here, so that's redundant. So we can be anything real except 0 plus pi n. So I'm just going to say n pi, right? Because it was starting at 0. Okay. Over to the problem. So personally, I think that the left-hand side seems crazier because it's much easier to square something than it is to try to take something and then make it squared. So I'm going to start on the left. Also, I think you can attack this two different ways. You can either square it first and then simplify, or you can try to simplify what's inside and then square it. I'm going to take a look at simplifying what's inside and then square it, because I know that looking at this, each of these denominators straight away. Oh, whoops, I just realized something over here, guys. This wasn't an x, it was an alpha. So I really should have written alpha is all reals, and alpha can't be that. Okay, so sorry, cotan is cos over sine, and then squared. Again, before I go squaring it, I'm going to simplify by putting this together. Because if it's one fraction, that's much easier to square. How do we square a fraction? We square the top. Check out how I'm leaving the top. And we square the bottom. Now, looking at where I want to go, my top should include 1 minus cosine, which is good. I actually have that. It's squared, but I have that. The bottom needs a 1 plus cosine, and it's in terms of sine squared. You guys know how to manipulate sine squared into a cos. Are you seeing how we can do this? The bottom is really 1 minus cosine. I'm going to factor it times 1 plus cosine, right? Difference of squares. And then I can cancel out 1 power of the 1 minus cosine, which is what I wanted to do. Anyway, there we go. You did it. Now, if you wanted to square it first, let's just say you squared it first. If you squared them first, you'd get cosec squared alpha minus 2 cosec alpha cotan alpha plus cotan squared alpha. Like, that's literally what happens when I square it. When you do that, you just, what you may notice, may or may not notice, is then, okay, then I could change, these are not Pythagoreans together, cosec squared plus cotan, it's not. So what I could say is, oh, well, I noticed that all of these are over sine squared, because like this cotan, this cosecant is really a sine on the bottom, and then this cotan has a cos on the top and a sine on the bottom. So that's how I get this, and one ends up being a sine squared as well. So what you'll notice, perhaps, is that these all end up being over sine squared, right? So like once you expanded it. So then I could put everybody together. And then you kind of get to where we were here. It's just that in the top, oops, this should be squared. It's just that in the bottom, obviously I'm going to follow the same pattern. In the top, it's a little trickier to see that this actually does factor into 1 minus cos times another 1 minus cos. Like that top does factor. And so then that could help you, get to this next step, which is basically here. And then I think from there, you guys can see it follows what I just did below. Okay. So there are more ways than one to solve these proofs. I'm just giving you some ideas. There's a lot of things that you can be looking for. We'll do some more in class, a little bit more in class, and then you'll start working on the quiz. Good luck. The more you do these, the better you will be. Remember, keep those equal signs, never cross out in proofs, and show me all your steps. All right, guys, see you in class.